Let's go ahead and continue with module 1.2, equilibrium constant and Gibbs energy, which is still part of physical chemistry 1311, the first module of our class lecture. We want to look at the following: equilibrium constant and Gibbs energy, relationship between Ka and Kc, the importance of equilibrium constant, then some illustrations and conclusions. Equilibrium constant and Gibbs energy. The reversible work done in compressing 1 mole of an ideal gas at temperature from a volume V1 to V2 is given by RT in V1 over V2. That's equation 1. But of course, from our first law of thermodynamics, delta E is equal to 0. Therefore, Q is equal to minus W. So we reverse equation 1. For Q will be minus. So instead of having ln V1 over V2, we'll have ln V2 over V1. So we'll have Q reversible is equal to RT ln V2 over V1, and that is equation 2. Now recall again from second law of thermodynamics that delta S is equal to Q reversible over T. So if we divide equation 2 by T, we will have R, that is T will cancel out, we'll have R ln V2 over V1. But again, delta G is equal to delta H minus T ds. So since T is constant and enthalpy is only a function of temperature, then delta H is equal to 0. Therefore, delta G will be equal to RT ln V1 over V2. So you can see that our delta G is actually equal to W reversible. Equation 1 and equation 4 are the same. Therefore, when an ideal gas is reversibly compressed at constant temperature, the work done on the system is equal to the increase in Gibbs energy. That's what that means, because equation 1 is equal to equation 4. Now, when we talk about this change from volume 1 to 2 at constant temperature, it means that delta G will be equal to RT ln C2 over C1. Remember the relationship between volume and concentration. V is inverse of concentration, and concentration is inverse of volume. So C2 and C1 are concentration in states 1 and 2 respectively. Therefore, that means delta G is equal to RT ln C2 minus RT ln C1. Now, assuming that C1 is equal to 1 mole, then automatically we'll be left with delta G equal to RT ln C2. So following this, if we drop the subscripts, 1 and 2, we'll arrive at equation 7, which is G is equal to G0 plus RT ln C, which is very important, as we'll see. Now, for a gaseous substance, we use that equation 7. G is equal to G0 plus RT ln C. So we'll now substitute for that hypothetical equation A plus B, giving us X plus Y with their stoichiometric ratios. We arrive at equation 9. We'll do the similar things and then put the equation together, and that gives us equation 10. And looking at equation 10, we'll see that ln X, concentration of XY over concentration of AB, is the same as K, that is the equilibrium constant. So that gives us equation 12, which is delta G0 is equal to minus RT ln K, or equal to minus 2.303 RT log K. This is a very important equation. It gives us the relationship between the equilibrium constant and the change in standard Gibbs free energy. Now we're looking at Ka and Kc. Ka is equilibrium constant in terms of activity, and Kc is equilibrium constant in terms of concentration. Now the Lewis fugacity rule states that the activity of any species in a mixture is equal to the partial pressure of the gas multiplied by the activity coefficient of the pure gas at the total pressure of the mixture. This is similar to Raoult's law, In this case, we are talking about activity and activity coefficient. So recall, we have used that equation before when we said equilibrium constant in terms of activity. So if activity is yp, we substitute, collect like terms, and we arrive at equation 13, which is Ka equal to Ky multiplied by Kp. So we can say activity in terms of, equilibrium constant in terms of activity is equal to the equilibrium constant in terms of activity coefficient multiplied by equilibrium constant in terms of pressure. So for ideal gases or real gases at zero pressure, Y is equal to 1, therefore Ka is equal to Kp. Now, if we use equilibrium in terms of concentration, which we have made this equation before, we now go back to our ideal gas equation and rearrange to make P the subject, and P will be equal to C RT. So we'll substitute. When we substitute, we'll rearrange by collecting like terms. We can see that CCCD, CACB is equilibrium constant in terms of concentration. So it means that Kp is equal to Kc bracket RT to the power C plus D minus A plus B. C plus D and A plus are the coefficients. That's the number of moles of the product minus the number of moles of the reactant. So we can say that Kp is equal to Kc bracket RT to power delta N. And of course, we can use this to identify the species. If delta N is not equal to 0, if delta N is equal to 0, it means that Kp is equal to Kc, because anything raised to power 0 is 1. So RT to power 0 will be 1. And then that means there is no change of number of moles going from reactants to product. But if it is not equal to 0, then Kp will not be equal to Kc. Of course, equilibrium constant is very important. It remains constant at its fixed temperature, and the magnitude of it determines the extent to which the reaction proceeds. Remember, it is the concentration of the products divided by the reactant. So if it is high, it means that product concentration is high. If it is low, it means that product concentration is also low. Now, generally, we can use the equilibrium constant. If K is greater than 1, reaction goes forward. If it's equal to 1, it is in equilibrium. If it is less than 1, the reaction goes backwards. We can also combine the Gibbs free energy with equilibrium constant to be able to predict the spontaneity and direction for chemical reactions. If delta G is equal to negative, the reaction is feasible. This means K is greater than 1. If delta G naught is 0, reaction is at equilibrium, so which means K is equal to 1. If delta G naught is positive, the reaction is not feasible, which means K is less than 1. So we can use these conditions to predict spontaneity and direction of a chemical reaction. Another illustration, we're using Kp equal to Kc bracket RT delta N. So we'll substitute all that is given. Just pause the video, look at the solution, and whatever you don't understand, put up a question and we'll put it through. Also, illustration 2, we're using that equation I said, very, very important equation. Delta G naught is equal to minus RT ln K, or minus 2.303 RT log K, to give us the same thing. So we're told to find, okay, in this one, we're given the delta G, so we're told to find the equilibrium constant. So whichever way, you can be given delta G, or you can be given equilibrium constant, and you're told to find the standard change in Gibbs free energy of the reaction. Here we are, the end of module 1.2. We've talked about equilibrium constant and Gibbs energy. We've looked at relationship between K and Kc. We also looked at importance of chemical equilibrium in terms of predicting feasibility and direction of chemical systems. And we've looked at some illustrations. Thank you very much, and see you in the next class.